Okay, this video is basically a supplement to video 1. I called it video 1.1. And in this video, I would like to talk about the rotation metrics. This is something that we will use to accurately define the rotation and displacement field in different beam theories. And this will put everything on a firm foundation. Um, So let's start. Let's say if you have a coordinate system in general, say xy, and then you have a point here, or let's say an arrow A, call it AI. Obviously, this will have a component, two components, say AX and AY in this coordinate system. So the coordinate system I am considering here is just general. You can have any uh, compatible right hand rule, maybe coordinate system. But the rotation matrix comes in this way, that if I come and rotate xy coordinates, but I'm keeping AI as is. So basically what I will do is, let's say this is my x, this is my y, and I rotate the xy coordinates to say x prime, y prime, while I am keeping my point, say A, or shall we say AI, intact. So in terms of, you can do it two way, but I will not go the other way. But if you want to refer to this is called passive rotation. So in passive rotation, basically you rotate the coordinates and then you keep the material point or the vector as is. Now in these coordinates, obviously the components will change. So if I come here, this will be my new components on the x prime y prime axis, which is different from that. Note that the AI is the same, the magnitude of AI is the same, but the component changes. So in other words, what we are saying here is that if I do that, then if I take the magnitude is the same, everything is the same, and then this A or AI, shall we say, is as the component of AX, AY, or component AX prime, AY prime. So we are basically representing the same vector in different coordinates, but the coordinates are related to each other by a rotation, a solid rotation. So if this angle is theta, therefore this angle is theta, although maybe not shown here to the scale, but this is theta. Now, what direction should the rotation is here? So if we go right hand rule, and then here I'm rotating xy coordinates, and if I'm implicitly assuming that I'm rotating about z axis, right? So because z axis is perpendicular out of the screen according to right hand rule. So if I use the right hand rule, I write it here again. My unit vector, shall we call it? I call it unit vector, which has the magnitude of 1, is along the z-axis, or shall we say it has components 0, 0, and 1 in my coordinate system. So this is the axis of rotation. This is the important part. So this is axis of rotation. For theta. Now you may say that I want to go to the opposite direction, and if you go to the opposite direction, so basically uh, you rotate by minus theta, shall we say, and the minus theta axis of rotation will be 0, 0, and minus 1. So how to find the uh, axis of rotation? You follow right hand rule, then you go x over y, and then your term will be upward or out of the screen, which is in the direction of the z. So that is in the right hand rule positive direction, shall we say, and that would be 0, 0, 1. And if you want to rotate about minus z direction, your rotation axis of rotation, including the direction of your rotation, will be 0, 0, and minus 1. Okay. Now we can go in this can go in three-dimensional, or for the sake of discussion, in any directional number of dimensions. But usually we go three-directional or three-dimensional space. So if this vector sits in the xyz plane, then the same thing applies. But we simplify it here for the sake of showing it as a sketch. Now, what are these components? How do we calculate these components? One can say, okay, I follow the geometry here because these two are the same, theta, and then I can quickly calculate this length with reference to the length which is here, if I want to draw it again here. So I don't want to crowd it, but let's say if I come here, this is your AX, and this is your AY, shall we say. I can connect these lengths through the geometry, but there is a better way of doing it. So there is a rotation matrix. When I say better way, I don't mean just another way, a more secure way without making mistakes. Rotation matrix. We call it Rij. And the derivation of this rotation matrix is out of the discussion, content of discussion here, but I give you the formula in terms of index notation. It is Ni Nj plus delta Ij minus Ni Nj cosine theta, that rotation, plus permutation symbol Ijk Nk sine theta. So this formula will give me a matrix. So N is the direction that we are rotating. As I mentioned, it is, say, for this case, it is 0, 0, 1. Cosine theta is the cosine of the angle of rotation, and this epsilon ijk is the permutation symbol that I described in the first part of the introduction. So let's work it out for this one. And therefore, I come here and I say ax prime, ay prime is r times ax ay. So basically you pre-multiply the vector which represents the components of the A by R, and then you will get your results. So let's do it here. First of all, let's work out R to give you some idea how these things are working. So Rij is, so the first component is N11. I will write the N here again to have it handy. So N11, which is first one is N11, which is R11. N11 is 0, okay? But delta 11 is 1, as we discussed it in the first one. The canonical delta, if the indices are equal, is 1. And then this is 0 again, Nij. So this will become cosine theta. And the permutation symbol is 0 because two indices are repeated. The second one, R12, is 0 because the the second component and first component of n is 0. Delta becomes 0, and everything n1, 2, 3. Okay, here we have to be careful. So this is 1, 2, 0. This is 0. This Ni, Nj is 0. 1, 2, 3. Nk is actually not 0. And I should, sorry, here you have to be very careful. This is not 0 actually, because N11 is 0, because 11 is 0. If I want to write it, this is N1, N2, N3. So 1, 2 is 0. Delta 1, 2 is 0. So the first two term cancels. But epsilon 1, 2, and then if I have 3, this becomes 1. And Nk is 1, actually. N3 is 1, sine theta. So I get the sine theta here. Good. And R13 is 0, delta is 0, 1, 3, and 2, because this becomes epsilon ijk is 1, 3, and this should be only 2, and this is 0. And then this is not symmetric matrix. You have to be very careful. R21 So R21 is 0 and delta is 0 and 2, 1. So this becomes epsilon 2, 1, 3. So 2, 1, 3 is minus 1. So this will become minus sine theta. And R22 becomes 0, but delta 22 is 1. So I get a cosine theta, and a permutation becomes 0. Okay, so if you work it out, this will be my case. So this 3, 3 comes out to 1, obviously, because we are rotating about the z-axis here. So there is the component in the rotated coordinates, and the original coordinate system is the same. So that is why this is coming out. So we can kind of take the two-dimensional one or part and then work it out. So if I come here and get my rotation matrix, and multiply it by ax, ay, what do I get? I get ax cosine theta plus ay sine theta. And then I get minus ax sine theta plus ay cosine theta. So this will be my new components, which are ax prime, ay prime in the rotated coordinates. You can do this for any type of rotation about any axis in general. And again, if you want to have a extended reading or further reading, you can refer to the reference that I gave you in the previous video, the introduction. We will use this for the beam theory as we will go forward to establish these rotations of the which are involved in each theory carefully and consistently. Thank you.